So today we're going to look at a shortcut for derivatives that's called the product rule. This is something that we use when we've got two functions that are being multiplied together. This is really going to help us expand the type of functions we can take derivatives for and make things a little bit easier, again, for finding derivatives for a little bit more complicated functions. So in this case, again, we're going to go through and prove how to find the derivative using this product rule. We're going to prove that the rule is true, and then I'll show you an example or two of how this product rule is actually used. We'll do some videos later where we do more derivatives and just use the rules and get some really good practice in with what we're doing here. So we've got a function here, we're going to call it h of x, and it's going to be the product of, h of x is going to be equal to the product of two functions. One of them we'll call f of x and the other one we'll call g of x. And we're going to go back to the limit definition again. We're going to see if we can prove what the derivative of this is going to be. So as always, since we're going to use the limit definition of derivative, we're going to take the limit as h goes to 0 of f of x plus h times g of x plus h. Again, just plugging in x plus h into both of these functions, minus f of x times g of x, all divided by h. So again, it's just the difference in the y-coordinate divided by the difference in the x-coordinate. Okay, so plugging in x plus h for x over here into the f of x function and x plus h for x here into the g of x function. Here's where there's a little trick to this one, and here's what the trick's going to be. I'm actually going to modify this just a little bit to get some information in here that I would like to use so that I can split this thing apart. So what I'm going to do is I'm going to take this function, limit as h goes to 0, and I'm going to leave this first piece the same, f of x plus h times g of x plus h. But here's where I'm going to add something in here. I'm going to add in here, actually I'm going to subtract first of all, minus f of x times g of x plus h. Okay, but when I subtract that out, I've actually changed the problem a little bit. So I have to account for that. And so what I'm going to do is I'm going to add it right back into the problem. So I'm going to add f of x times g of x plus h right back in. So notice that when I subtract this and then add it right back in, I'm actually adding 0, which seems like a silly thing to do, but it's actually going to be really helpful for us here. So I've added these two pieces, and then of course I still have plus, minus f of x times g of x. And I ran out of room there. Okay, so I've just in the middle of this right here, I added 0 using subtracting f of x times g of x plus h and then adding it right back in. Of course, this is all still divided by h. Now, I'm going to kind of manipulate that around a little bit, and rather than rewrite that function to start with, I'm going to separate this out a little bit because I actually want to use this in two different ways. So what I'm going to do is I'm going to split this into two fractions, and I'm going to put that part over h, and I'm going to put that part over h. So notice, and this plus here is just going to be between those two things there. Okay, so really all I did here was take a large fraction and divided it into two smaller fractions, something that's perfectly legitimate to do. These have a common denominator, so if I wanted to, I could combine these back together and get it to look like this again. So I haven't changed the problem any at all. Now, I'm going to work with this first one here to start with, okay, and I'm going to make sure that we know that we're still taking the limit of that whole thing. I'm going to start with this first piece here. And what I'm going to do, notice that this term and this term both have a g of x plus h. So I'm going to factor that out and just kind of put it off to the side. That's going to get me the limit as h goes to 0 of g of x plus h times f of x plus h minus f of x divided by h. Notice that if I distribute that g of x plus h back through this parentheses here, it's going to give the g of x plus h to both of these, which will get me right back where I was here. I really just factored out the g of x plus h. Okay, I'm going to do the same thing over here with the second fraction. Notice that in both of those, I have an f of x here and I have an f of x here, and so I'm going to factor that f of x out and leave it off on the side as well. So I have f of x, and when I take out that f of x, I get left with g of x plus h minus, when I pull the f of x away here, I get left with g of x all divided by h. And again, you can see that if I redistribute here, if I put the f of x back through this fraction here, it's going to get me back to what I had over here. So again, I haven't changed the problem here at all. Now, here's where our properties for limits comes into play. If you remember when we were talking about limits back in some earlier videos, we talked about the fact that the product of a limit was the limit of the product, and the sum of a limit was the limit of the sum. So this limit can actually be applied to each one of these things individually. So let's do that. Let's apply the limit individually to these things. If I take the limit as h goes to 0 of g of x, that's going to get me, as h goes to 0 of g of x plus h, that's going to get me g of x. Okay, so in other words, when h is 0 here, if I plug in 0 for h, that's going to get me g of x. On this second piece here, and this is the really fun part of this, if I take the limit as h goes to 0 of this second piece here, that actually is the limit as h goes to 0 of f of x plus h minus f of x divided by h. That's the limit definition of f prime. So that right there is just the derivative of f. Okay, and then I'm going to go to the next term, and I have the limit as h goes to 0 of f of x. There's no h there at all. And so I can just leave that as f of x. And then for the last piece here, I have the limit as h goes to 0 of g of x plus h minus g of x, all divided by h as well. That's the limit definition of derivative for g. So this is going to be g prime of x. And so it turns out, and so most of the time we write this just a little bit differently. These things are the multiplication's commutative here. So I'm just going to rearrange this just a little bit, and I'm going to say, okay, that's the derivative of the f function times the g function plus the f function times the derivative of the g function. Okay? The fast way that I always remember to do this was, if you want to take the derivative of two things that are being multiplied together, so this is h prime, if I want to take that derivative, then I take the derivative of the first term, the first function, multiplied by the second function, and then add that to the first function times the derivative of the second function. And that's what our product rule is. Derivative of the first times the second plus the first times the derivative of the second. So let's see what this looks like as we just look at the function in general here and actually put this into some practice. So there's the proof of it. Let's actually look at a function or two and see if we can show how this works and what the application for it actually is. So let's say that we've got a function f of x, and I have, let's do the square root of x times x plus, let's do x squared plus 3x. Okay, so we've got two functions that are being multiplied together. I have the first function is the square root of x, and the second function is x squared plus 3x. So if I want to find f prime, according to my product rule, I need to take the derivative of the first function. Now keep in mind that that square root of x can be rewritten as x to the 1/2. So I'm going to rewrite that as x to the 1/2. And then so when I take the derivative here, I get the derivative of the first function. That's going to be 1/2 times x to the negative 1/2 using my power rule. So that's the derivative of the first function times the second function. Not going to do anything to that at all right here. Plus the first function, don't do anything to that. times the derivative of the second function, and I'll just use the power rule that we looked at before to take the derivative of this. Derivative of x squared is 2x, plus the derivative of 3x is 3. And there we go. There's our derivative for this function here. Pretty straightforward. Again, just take the derivative of the first function times the second function plus the first function times the derivative of the second function. Okay? Now, let me show you something that hopefully this will kind of connect the power rule and the product rule and kind of verify for us that what we're doing with this product rule is actually true. Last time when we were working with the power rule, we were taking functions and just maybe something like x squared plus, let's do x squared plus 3x plus 2, and we were finding using the power rule that that was going to be equal to the derivative of x squared is 2x, the derivative of 3x is 3, and then the derivative of, we didn't really talk about this, we'll do this a little bit more later, but the derivative of a constant function, remember that this is 2 times x to the 0, and when I apply the power rule to that, 0, I bring the exponent down, so I have 0 times something, so that's just going to be 0, it goes away, and actually turns out that the derivative of every constant is going to be 0, so that just drops off completely. So what I want to do here is I'm going to actually factor, I'm going to do this same problem again, but I'm going to factor this, and hopefully you'll agree with me that this factors as x plus 2 times x plus 1. And so now I have the two functions that are being multiplied together. So what I'm going to do is I'm going to use the product rule to differentiate this one, and hopefully what we find is that we actually get the same thing that we have here. So let's take the derivative of this one using the product rule. So we're going to take the derivative of the first function. The derivative of x is going to be 1, and of course the derivative of 2 is 0, so that drops out. And I get left with x, so the derivative of the first function is 1 times the second function, x plus 1, plus the first function, which was x plus 2, multiplied times the derivative of the second function. Derivative of the second function is going to be 1, and then the derivative of the constant 1 is 0. And so I end up with this piece right here, the derivative of the first times the second plus the first times the derivative of the second using the product rule. And now I can, of course, the 1 times x plus 1 is just x plus 1. The 1 times x plus 2 is just x plus 2. Now I can combine like terms here, and I get 2x plus 3. And notice that it's the same thing that we got using the power rule. Now, for a problem like this, it's always going to be easier to just go straight to the power rule here. I just wanted to kind of show you that the product rule is giving us the same result. We're actually going to use the product rule when we've got more difficult functions to work with, like trig functions and transcendental functions, any kind of transcendental function at all. That this is going to help us make find the derivative a lot easier using the product rule when we couldn't do it when we're working with polynomials like this. Okay, so this is just a real quick example of a couple of problems using the product rule. We'll go back through these a little bit later in some later videos and get some more practice with this. But the proof that we showed you here is how the product rule came about, where it comes from, and why it works the way that it does.